Hello everyone, welcome once again to my YouTube channel. Today we'll be looking at time series forecasting in machine learning, and the aspect we'll be looking at is predicting the future. Now the data set we are looking at is a time series data set containing information, a daily basis information from 2020 to 2024. So we'll be forecasting the number of visitors we should expect in 2025. So this is the summary of the data set and the project. Sit back, relax, and enjoy the teaching.
Now, this is our time series analysis on Jupyter Notebook. The time series we're looking at is the SARIMA time series. Now, the question is, what is SARIMA? We have SARIMA, we have ARIMA, we have Facebook Prophets. These are examples of time series forecasting models. Now, what is SARIMA? SARIMA forecast, this means S stands for seasonal, A stands for autoregressive. That is, the AR stands for autoregressive, the I stands for integrated, the M stands for moving, and the A stands for average. Now, let me break it down. The SARIMA is spelled SARIMA. And we can see that seasonal means, because we have ARIMA and we have SARIMA, the difference is the S. Now, what does the S stand for? Seasonal. What is seasonal? Now, it depends on the data set. Now, for example, if you are dealing with sales, we know that depending on the kind of sales you are doing, if during Christmas you have more sales, that means that your data set is seasonal. So there are seasons. During Easter, you sell more. So if you are to forecast sales with that, your sales under your data set, then you are supposed to use the model called SARIMA. So it will take into account the seasonal patterns in your data set. Then the autoregressive, it means, what does autoregressive mean? Autoregressive means the information of today, or the data for this point or for today, is dependent on yesterday's information or yesterday's data. That is the meaning. Then integrated stands for example, depending on how your data set is, you might need to apply differencing. Now, what is differencing? Now, what differencing does is that it makes your data set stationary. That is, it removes trends from your data set. It makes it, we kind of like say, something like on a straight line. It's something like, okay, it removes all those spikes in your data. It removes those obvious sales in Christmas. So it makes everything equal. That is, it takes away those extraordinary times in your data. So for example, it will tell you in Christmas, if you apply difference into your data set. So for example, it will tell you in Christmas time, the sales are still the same with every other day. So that is what it's trying to remove bias from your data so that it can be able to adequately forecast for next year or for next month, depending on the forecast you want to do. So this differencing is a feature engineering. So you're engineering your data, you're working on your data set to remove bias. Then finally, the MA, which stands for moving average. What does moving average do? It takes into account errors in the past in your data set. It calculates the errors in your data set. As we go, you will see the residual errors. So it calculates it and takes into account the errors. So, for example, today's information is dependent. Today's error is dependent on yesterday's errors. So that is the full meaning of SARIMA. So let's proceed. Okay, so now these are the libraries we imported: the Pandas, NumPy, the Matplotlib, and Seaborn. These are for displaying your charts, the stats models, and so on. So this stats model is responsible for the SARIMA, for plotting the charts we'll use in our SARIMA models, and so on. So the cell 2, we loaded our data set. Now cell 3, when you are dealing with time series forecasts, it's important you convert your date column to date time. Date time is a data type in Python. Just like you have the integer data type, which deals with your whole numbers. You have the float data type, which deals with your decimal numbers, and so on. So to date time is a data type. So you convert your date column to date time. So that is what this cell 3 did. And we sorted it from the first day to the last day. Then we set the date as index. Why are we using date as index? Because it is unique. It is unique. If you look at the data set, you will discover that the date time is unique. So let's look at our data set. So this is our data set. This is the same data set we used for the previous videos. I will send the link. In the previous videos, we looked at other machine learning model. We used linear regression, support vector regression on this data set, and we got our results. So this time we are using a time series forecast on this same data set. Okay, so look at it. So every day, that is every row on this data set is unique, meaning the date information for each row is different from every other row. So we can see this first row is saying 1st of January 2020. The second one, 2nd of January 2020, like that. So using the date as the index is very accurate. So it's okay for us to use it. Okay, so having looked at the data set, understanding why we're setting our date as the index. So let's move. So let's look at our data set. Let's plot the data set to see how it looks like over time. So that is what this cell 4 is doing. It's plotting our data set, the target column. The target column is the PAC visit count column, which is the last column. And so that's what we are plotting over time. So we want to see the number of visitors per year over time. That's why we are using our line charts for it. So here it is. So you can see it from 2020 to 2024. It's within a range. It has been ranging. It's within a known range. So you can predict, okay, the number of visitors are within 0 and 250. But all of a sudden, in 2024, there was a sudden spike in visitors. So you can see what happened. So throughout 2024, it was within that range of the spike. So that is what this chart is telling us. So you can see this is part of exploratory data analysis. So we're trying to explore the data using charts to see how it looks like. So we can see this sudden spike. Okay, the next thing we're going to explore in this data using our histogram is to check for skewedness. Now, what is skewedness? That is, oh, the data is skewed. Now, we can either check, it can either be right skewed or left skewed. Now, what does that mean? Now, from this data set is right skewed. That is, it goes up and then forms a tail to your right-hand side. Look at the line on it. It goes up and forms a tail to your right-hand side. So this data set is right skewed. The meaning of this is, and it's just so terrible, it's so obvious. From this, you should know that time series forecast will not be the best for the analysis of this your data, but let's proceed. Now, the idea is just to see how to use time series on your data set. How to use time, how to forecast. That is just the idea. So let's ignore the fact that the data set is right skewed. So let's continue. But also, since we know that the data set is skewed, we'll still try to apply difference into the data set. So let's proceed. So cell 6 says we should check for the trend on the data set and the seasonal pattern on the data set. So that is what we're going to be doing here. So for me, I had to put the trend and the seasonal information into a table for further visualization in Power BI. Okay, so this cell is visualizing our data, the park visit count data, because for this time series analysis, we'll be looking at only the park visit count data, that is column. Okay, so look at it here. The normal one we've already plotted, as in plotted. So anytime you want to do this, you use the decomposition. This is the decomposition, seasonal decomposition function. That is what we are using. So the next chart is plotting it over time. That is trend. What is trend? Trend just shows the direction of your data. Is it going upward or is coming down? So we can see our trend from here shows that our data set was stationary, was in a particular range for a long period of time before all of a sudden it went up. Then the seasonal pattern in our data set is showing from up, it went down, from up, it went down like that. So that is what is showing us here. So then our error, this is our error over time. Our error over time. Our error is supposed to be normally distributed, but we can see the error is not looking nice. But anyway, we'll still proceed. So now cell 7, we're checking for the ADF. That is, sorry, we're checking for stationarity, which I've already explained earlier. And we're using the add Fuller function, add Fuller model of or function to check for stationarity in our data. So when we call it, we check for it on our data set. Now, for you to know if your data set is stationary or not stationary, we look at this. Now, this is a test. Is a test that we're doing on our data set. It's an hypothesis that we're checking for. So we're checking, is it stationary or not? So if our p-value is less than 0.05, then it is stationary. So let's run this. So once we run this, look at the result we got. So our p-value says 0.8. 0.8 is greater than 0.05. So once you notice it in your data set, the next thing to do is to apply difference into your data set. Just like in linear regression, you apply standard scalar. In time series, you apply differencing to your data. What does differencing do? Is you are trying to make your data set to be normally distributed. What does it mean for your data set to be normally distributed? It means it started from the bottom and went to the top and came down. I've explained this in my previous video, machine learning video, when we're modeling with linear regression and so on. I'll drop the link in the description. Okay, so having applied differencing, which apply the ADF test again, that is cell 9 now. And we checked. When we apply the ADF test again, so we are checking, okay, what is our result now? We can see our P is far less than 0.05. You can see this minus this E minus 18 means it is 0.00000 up to 17. 2. So it's far less than. So now our data set is what? Stationary. So now that our data set is stationary, now we can build our model. So first and foremost, when building your model in SARIMA or ARIMA, you take into consideration your ACF and your PACF. Now, since our data set is now stationary, we determine the SARIMA parameters. And your SARIMA parameters are your ACF. What is ACF? Autocorrelation function. This autocorrelation function is related to your moving average, MA, moving average in the name, SARIMA. So this ACF function check for the MA, the value you are going to use for your MA. Why this PACF, this partial autocorrelation function, is in charge of the autoregressive, the AR in your SARIMA. So it checks for the autoregression, which I've already explained earlier. Autoregression means today's information is dependent on yesterday's information. So now to do that, to get the value for your ACF, and your PACF, you have to plot it in a graph, or to get the value of your MA and your AR, you plot the ACF graph and the PACF graph. So that is what this line of code is. You plot ACF and you plot PACF. So now this is our graph here, the ACF and the PACF. So now how will you know your value for your ACF here? This is 0.0 and this is 0.1. So what you check in your graph is to check where there's an obvious spike in the data that is in your chart. You can see all these ones are within this blue range. There's no obvious movement out of it. But at 0.0 and 0.1, there was an obvious movement out of this range. So our ACF value will be 1, that is 0, and the last one, 1. If there was another serious spike somewhere here, this will be number, I think number 9, if we count it, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our ACF will be number 9. So for our ACF, we're going to be having 1. And the same thing applies to your PACF. Our result will be 1. The reason why we're not going to take 2, 3, 4, 5, or 5 is because it just panned out. From here, it just slide down a little. So it's not so obvious. So we are going to take 1. So our ACF and our PACF value is 1. So now we come to our cell 11 here. We're going to define the other parameters. Okay, so let's continue. So we've seen the chart. In case the chart is not well understandable, maybe you're not understanding where to pick the lag from, then you can use a hyperparameter tuning function. So in this situation, we'll be using the grid search to determine the best parameters. We're using the grid search. So before we proceed, let's look at our SARIMA parameters ranges, our SARIMA parameter ranges. Okay, so now we have our SARIMA parameters to be these: PDQ, that is small letter, then PDQ, capital letters, and S. The PDQ, this stands for the non-seasonal components in your SARIMA. Why these capital letters stand for your seasonal components in SARIMA, and the S stand for the seasonal cycle. So now they are all defined here. So on a normal day, we can decide if we don't want to use this hyperparameter tuning, the grid search, we can say our P is 1 and our Q is 1. The P stands for the AR, autoregressive information, and that can be determined from here, the PACF. While the ACF stands for the moving average, that is your MA terms. So if we're to go with this chart, our P should be 1 and our Q should be 1. Then our D, which is the differencing order, how many times did we perform differencing? If we go back, we can see we performed differencing only once. We checked for stationarity. It was not stationary. We performed differencing and we found that it is stationary. So our differencing is only 1. Then how did we come about this capital letter D, the difference in the seasonal differencing? Well, most of the time, the most common number used is 1. So there's no need for us performing the seasonal differencing. But if we are to perform the seasonal differencing, then we can add it to our differencing function here. So all we need to do is just take this, copy, paste it here, and put it here. So inside this box, we are going to be having 7 because our differencing circle is 7. We chose 7. Now, what does 7 stand for? 7 stands for weekly. What does weekly mean? It means, let's go back there. So S is 7. So it means every week there is a possibility. For example, we're trying to say every week we expect a spike in visitor, maybe once a week, maybe over the weekend. That's when we experience more visitors because this data set deals with park visits. That's the number of visitors that come to a park. That's what this data set is trying to predict. So we're trying to look at it in a seasonal, that is weekly basis. But if we change this 7 to 12, it means our seasonal cycle is monthly. That is, the spike happens monthly. So maybe at the middle of the month, we experience spike in visitors. You understand? So that is what all this stands for. Then the capital letter P and Q is for the seasonal AR and MA terms. So we're not using the charts. This time we are going to be using our grid search. So whatsoever our hyperparameter tuning function, which is grid search, gives us, that is what we are going to use to fit out, to run our model. So let's proceed. So now we define our best parameters. So our best parameters will be this parameter combination. So these iter tools will be looping through it to do the combination. So we try it on our model and we'll check for it. So look at our SARIMA model, it has been called, and look at our data, our column, that's our data, the park visit count. So we have our order parameter 1 and so up to parameter 6. Look at it here, 1, 2, 3, 4, 5, 6, 7. Take note, it's there from 0 to 6. So that is for that. No need for check for stationarity. So we fit into our model and we check for the best parameters. So once the best parameter is checked for, it prints out the best parameters. So these are our best parameters here. And these are the parameters we'll be fitting into our model. So now it's time to train our model. So we're training our model with the best parameters. So here's our model. And we're putting in the best parameters here. So it runs the model and it fits the model here. Okay. So now since our model has been fit, we've created our model, we've trained our model in cell 13. So now it's time for us to forecast in our cell 14. So what is our forecasting? We want to forecast for the next year, which is 2025. We want to forecast for the next, and the year is 365 days. So here, this is the function that gets the forecast. Then we decided to extract our values from the forecasted information. And we decided to put everything in a data frame, that is in a table format. And we saved it as a CSV file. So now let's plot our results, our forecasted values. So take note, this is the file in which our forecast is written. So we're going to look at it to see the forecasted information. So we are plotting our forecast versus our different original data sets. Let's take a look at how it is in a chart format. So don't forget, we're plotting it against the difference data set. That's what do I mean? This park visit count has already been differenced. What we have been working with is the data set that has been differenced already. So we want to check how our forecasted values is, comparing it to the original data set. That is the data set has undergone differencing. Let me show you where I did the reassignment here. Look at where we performed the differencing here. So when we performed the differencing on the original data here, I reassigned it to that same column in my data set. And so anytime you see this, you know the information in this data set or this column has already been differenced. So let's go to our chart to see how it is. So we plotted it as a line chart, and let's see how our chart is. So it's a 365-day SARIMA forecast. So these are our forecasted value is the red, and our actual value is the blue. You can see this pink box. This pink box is your confidence interval, which we calculated here. Now, confidence interval in a layman term is just like the range we should look at. Fine, this is our forecasted value in the red, but we should look at this. This says plus or minus. This is what we should look at. So, for example, if at this point here, what we're having, the forecasted visitor for, let's say, January 2025 is 300 visitors. Then we can say, okay, if the forecasted value is 300, so from here to this point, depending on the number that is there, we can be saying, okay, we're looking at maximum of 400 visitors and minimum of minus 400 visitors. So when you are planning and budgeting, you do within that range. So looking at this, looking at our chart, you can see the different data set. You can see it's no more looking like the original way. Let me take you back to the original chart, how it looked like. Look at it here. You can see it was ranging, then all of a sudden a spike, but now it's no more looking this way. So this is how it looks like now after it has been differenced. So this is how it looks like, and this is where our range, our value is ranged. So it's between plus or minus 0 to the number and to this number. So you can see our result is around 0. Our result is around 0. Don't forget, this our data set is not well distributed. You can see that it's rightly skewed. So we will not expect the best result from it. So now we are going to look at the result we got. Let's look at the result we got. How our result is. Okay. So this is the predicted park visit for 2025. So for January 1st, 2025, we're expecting about 285 visitors. For January 2nd, we are expecting minus 1.4 visitors. This is not supposed to be. Take note, our data set is not so nice. So in conclusion, from the results we are getting, we can see that this SARIMA model is not so good for our data set. In our next video, you will see how we'll test using our metrics, our mean squared error to check, to further know if this SARIMA model is okay for this data set.